door neighbors at the ICFP poster competition. Nice to meet you, I'm Sam.
I'm Harry.
Oh my gosh, I love your poster. What is it about?
Oh, let me show you. This is a poster on free generators. Free generators are a tool that we use in property-based testing that I was working on that allows us to view a generator of random things as a parser. So if you think about it, a generator kind of can take a bunch of random choices, but you could also think about it as parsing those choices into a value, and that's what free generators formalize. If you don't remember what property-based testing is, if you have some property that you want to be true about a program, for example, that inserting into a binary search tree maintains validity, then you can write a random generator that produces a bunch of binary search trees and use a tool like QuickCheck to test that the property always holds. And what free generators do is allow us to decompose a generator. Instead of just pulling a value out of thin air, we pull some random choices out of thin air, and then we make those choices. Free generators are formally based on a freer monad, which is kind of like an abstract syntax tree of a monad program. And there's one operation called pick, which is either interpreted as a random choice, or it's interpreted as parsing the first choice in a sequence. And when you write a free generator, it looks just like a normal monadic generator, but now you can do some extra cool things with it. For example, you can manipulate the random choices after you've made them, but before you've parsed them, which allows for some cool manipulation of values.
Wow, that's really cool, thanks.
Is this your poster?
Yeah. Do you want me to tell you about it? Cool.
Yeah.
So it's all about composing bidirectional programs monadically. And bidirectional programs revolve around bidirectional transformations. And this is one piece of code that can be run in two directions and is normally expected to satisfy some sort of round-tripping property. For example, my two directions could be transforming to and from different representations of the same thing. And my round-tripping could say that going there and back again is the identity function. This is really useful because it saves time, maintenance effort, and it saves the issue where you've got two pieces of code and they become out of sync. So the classic example here is a biparser. This is one piece of code that can be run forwards as a parser or backwards as a printer. I suppose these are actually a bit like your free generators, except this time the randomness being parsed is a string and what's being generated is an AST. Anyway, these are normally written using combinators, so you can think of lenses. But Liao et al. Make this more expressive by allowing them to be written monadically. And this is achieved using partial monadic profunctors. So profunctors are a standard construct from category theory, generalizing ordinary functors or structure-preserving maps. And they support both co- and contravariant operations. So in Haskell, they're realized as this type class, where the operations are called lmap and rmap. So you might actually recognize rmap under the better name of fmap. So the example here is the function arrow, because it's contravariant in B and covariant in A. And here, lmap and rmap are pre- and post-composition, respectively. So a monadic profunctor is one that's also monadic in its second parameter. Now, bear with me, I'm going to get a little bit technical, but I think it's worth getting to grips with this. So for example, if I wanted to make my biparser like this, it would be something like this. So this is a profunctor in B and A, and monadic in A. And it works by combining together a parser, which is already monadic, with a printing function. And this is a mixture of the reader and writer monad. So this biparser can either be run forward to parse a string into an A, or it can be run backward to print a B. And I suppose this scheme makes most sense when the biparser is aligned. And that's when B and A are the same type, because then we're parsing and printing the same thing. And here, the printing function is just the identity function, which also produces a string representation. And this structure is important because we can compose this monadically. So for example, if I had a biparser for letters and one for numbers, and I wanted to make one for letters or numbers, or this Lorne type, it might look something like this. But this has a few new things to it, so let's roll it back to something more familiar.
Hang on, wait, how'd you animate your poster?
Mirrors.
Oh.
So this Lorem type is a biparser for a letter or a number, and it's written in 2 halves, and each half is combined together using the alternative or construct, so that's that little bar thing. And if we focus on each part individually, it's built upon the letter and number sub-biparsers. So for example, number is going to produce a number n, and that gets passed along and then wrapped up in the number constructor. For those familiar with monadic and alternative programming, this seems like the natural solution. But remember, we're no longer programming with just monads. We're programming with partial monadic profunctors. So we can't get away with just using the monad interface. We also need the partial profunctor operations. So let's explore why we need the partial profunctor operations, starting with the profunctor ones and then going on to the partial ones. So the profunctor operations, they're motivated by the fact that this expression doesn't quite type check. And that's because bind only operates on the second type parameter of the profunctor. So in the number case, bind is expecting its first argument to have biparser lorem int as its type. But that's not the type of number. This means we need some function that is going to change the first parameter of the profunctor. Luckily, that is exactly what the lmap profunctor operation does. So lmap can fix this type error if given a function from lorem to char or lorem to int. And more generally, we call these functions that we give to lmap our backward annotations. And when programming with partial monadic profunctors, these will always appear on like a subcall or a recursive call. And there'll always be some sort of projection function from a bigger structure, in this case lorem, to a smaller contained structure, in this case int or char. And now let's motivate why we need the partiality by considering what happens if we give our L annotation a number or our N annotation a letter. So currently that can't quite type check. So that's why we need partial monadic profunctors, because partial monadic profunctors can have partiality injected into the first type parameter of the profunctor using this function called prune. And now our annotation functions can be total, because they expect to have the type lorem to maybe int or lorem to maybe char. And that's how we do it. That's how we compose bidirectional programs monadically. Oh, we also have this generator example that might be of interest to you. So bigenerators can be run forwards as a generator, like normal, but they can also be run backwards. And when they're run backwards, they check whether a generator could have made that value. So this is particularly useful for generators like your BST one, because that bakes in what it means to be a valid binary search tree. So now the bigenerator can be used as a checker for that value.
Yeah, that's really neat. I actually think that if we combine partial monadic profunctors with free generators, we could solve a problem that I've been thinking about.
Oh, tell me more.
So you know how in property-based testing, sometimes you have to shrink values, right? Sometimes the values that you have are too big, it's hard to debug, and you don't know what part of the value causes the problem. Often this is a manual process of figuring out how to shrink the values. There's some automation that can be type-based, but ultimately, when you have really complex situations, it's hard to shrink values. And there are some tools, for example, that are used in Python's hypothesis framework that use the generator to help in the shrinking process. And so, you know what, let me draw some stuff to give you an example of what I'm thinking about.
Oh, wow, you're really good at drawing. That's like a professional PowerPoint slide.
Thank you. So in this example, we've got some analyzer for like node packages, right? And so you've got these JSON files which define what a node package, you know, in JavaScript is, and it's got a bunch of data in there, and we're going to do something to analyze that stuff. But like, say a user comes to us and says, hey, this JSON file I have breaks your code. Your code doesn't work anymore. And the problem is, it's really big, right? This JSON file is too big, and you don't know what part of it is actually causing your code to fail. What you'd like is to be able to shrink that file down, sort of blow away a bunch of the fields that don't matter, keeping the important parts of the structure, and isolate the part that is actually causing the bug, in this case, rogue dependency. But you don't want to have to write this manually, right? You don't want to have to figure out how to safely shrink a JSON file. And so instead, you want it to be automatic. And if you think about the whole free generator thing, since generators are parsers, what if instead of shrinking the value, we would shrink the choices that would produce that value? This is a technique developed by McIver and Donaldson. Like I said, it's in Hypothesis. And it's like super cool, really works, except there's a problem here. It doesn't actually work for us because this value came from the user. We don't have the choices that produce the value, and so we can't do this internal shrinking process. If we had some way of going backward, of getting the choices that would produce a value, then we could do the shrinking process the way we want. And actually, I think a generator running in reverse is exactly what we need here.
I think you're exactly right. So remember how I said that bigenerators could check whether a value was generated by a generator? I bet we could also get them to return the choices that led to a value. Have you got your free generator code?
Oh yeah, I can pull it up.
Nice. So the main operations that bigenerators need are the partial monadic profunctor ones, right? So that is bind, lmap, prum, all those guys.
Oh my gosh, you're so fast at typing.
So the freer monad, right? That means that free generators are already monadic. So I suppose we don't need binder return, but we are going to need an extra type parameter. And while we've added that, let's get a little bit more intuition about these type parameters. You can think of the first one as sort of our overall result type that we want, and as the second one as a sort of intermediary value that we need to change because it supports bind. So now I've added that type parameter. I can add the partial profunctor operations into this type. So like free gen, the name, it doesn't really work anymore. It doesn't quite make sense. But what about reflectives and R? Because these generators reflect upon the choices that they've made.
Oh, that's very clever.
It's almost as if you came up with it. So let's make that change. Oh, awesome. Shall we see if it works? So let's do the BST example. Let's see if we can convert that to one of these reflectives. So first things first, we're going to need to change the type because we're now working with our reflective things. And you know what? I reckon it's worth sort of sticking to this interface because we know and love the quick check interface. So let's make our own versions of frequency and choose. Next, we're going to need to add our backwards annotations. So let's focus firstly on the ones on return. So let's put my bigenerator hat on. What I want the function that you give to lmap to do is just make sure that only a leaf value could have been produced. So let's introduce failure of prune and give the function that does that to lmap. We're probably going to want to do this like every time instead of return. So let's tidy that up into a combinator. Now let's think about the other annotations, the ones in the node case. So the ones on the subtrees and the number that lives in the binary search tree. So I reckon we want them to look something like this. So the function that's given to lmap is going to be focusing in on the value that subgenerator is creating. So in the node case, it takes in a node and it's just extracting out, say, that number that lives in the node. It's like focusing on the value that it's generated. It's a projection function, isn't it? So I think we could tidy this up a bit more. Why don't we use a lens? And if we use a lens to focus in, because the lens people are really clever, that means they can be automatically generated. So that focusing function, underscore node, can just be automatically generated. I think this is really cool. Oh, we're using freer. So this means all we've done so far is build up a syntax tree. So we better write an interpretation for it. Let's start easy. Let's start with a generate interpretation, because we definitely want this to still generate things. So what about something like this? For the interpretations of bind and return, why don't we interpret them as return and bind for gen? Yeah? And then for pick, What did you do for pick?
Oh, we just interpret pick as frequency in the quick check gen monad.
Oh, that makes sense, because then you can use the sub-generators and the weights. And then, so I suppose generation doesn't really use the backwards direction. So for the partial profunctor operations, we can just ignore those annotations and recurse. Shall we see if it works? Yay, it does. Those are both binary search trees. But we didn't really use the backward direction. So I reckon we also want to get a check instance, because that's the other half of biparsers. Let me quickly do that now, and we can check it using these BSTs, but I'll break the second one to make sure it says no. Huh, that works. Awesome. Does that give you what you need?
Yeah, I think so, right? If we think back to the picture, what we can do is while we're checking a value, we can keep track of the choices we're making. And so we can go backward and get the choices from a value. And concretely, what this is going to look like, the word backward is a little bit of a misnomer here. What we're actually doing is running the generator forward, but keeping track of what would happen, what choices we would make if we were generating a value that we're following along with. And those focusing annotations allow us to focus in on parts of the value so that we can analyze the choices. So we'll focus in on the first part. Here's some choices that we need to make. The next part, some more choices. The last, and so on, until we get a set of choices that would produce the value. This may not be a unique set of choices, by the way. It could be that multiple sets of choices map to the same value, but we really only need one for the shrinking that we're going to do, right? Because once we have a set of choices, we shrink the choices, which happens once and for all. We can write a routine to shrink choices without knowing anything about the underlying values, and then we can do this internal shrinking procedure. And actually, now that we've got all of this, we can do even more with this. Reflective generators are still generators, and so we can use them for generation algorithms as well. There's this thing called inputs from hell, which is an example-based tuning technique. Basically, you provide a bunch of examples that you think are common examples your application may see, and then you try to tune a generator to produce more examples like that. And I think we can use reflective generators to extend that algorithm to a broader set of generators. Basically, if we think back to the shrinking example, instead of the user giving us one thing, they're going to give us a bunch of things. And instead of, when we go backward, just extracting a set of choices, now we're going to extract weights on choices. We're going to determine frequencies of choices that need to be made. And then we can run the generator forward again with those updated frequencies to produce more values that are like the ones that we started with. And this is more expressive than the stuff that the inputs from hell folks did, because they were working with grammar-based generators. And grammar-based generators are really cool, but they can't express things like, for example, binary search trees. And so, since reflective generators are monadic, they can capture a broader class of preconditions that we might want to write generators for.
Well, that's really cool. I wonder what else. So I bet that it could also, am I on?
Are you?
Am I? Hello?
Yeah, you're good.
Okay, nice. I bet it could also complete values with holes in them.
Oh, that's really cool. It can also parse things, right? It's still a free generator.
And do the opposite. It can unparse things.
It can do that weighted generation thing that we were talking about.
What about enumeration?
Yeah, it can all. Wait, hang on, wait. We're getting ahead of ourselves here. How do we know these things are correct? What does it mean for any of this to be correct? Well, so first there's correctness criteria for the interpretations, right? We need them to be partial monadic profunctor homomorphisms, and there's details on that in the paper. And we also want to make sure that each reflective generator is itself sound, because you can write an incorrect annotation in your reflective generator that type checks. And so we have these soundness and completeness properties. Soundness means that if we can generate a thing, then we'd better be able to reflect on the choices in it. And completeness says that if we can reflect on the choices in something, we had better be able to generate it. And since we're doing property-based testing, why don't we make sure that we can actually test these properties? And it turns out we can. There are properties that you can test and apply to your reflective generators to make sure that they're both sound and complete. And we should also think about what reflective generators can't do, because they do require a little bit more work, right? The first thing they definitely can't do is generate a thing and then throw it away, because we need to be able to go backward at every step. We need to be able to get the value out of the thing out of the continuation. And a little more interestingly, recovering information has to be decidable, because this is a generator here for, say, system F subterms. You generate a type, and then you generate an expression of that type. But in order to go backward, you have to do type inference. And so in cases where type inference is undecidable, you actually can't always go backward. And there's a few more limitations, but in practice, we can write all the generators that we actually want to write with reflective generators. There's just a few little caveats in the way you have to frame it.
Gosh, it sounds like this has got a lot of potential. And I bet it could branch out into future work, like automating the conversion from normal generators to reflective ones. Because currently we got to do that by hand, and we got to write those backward annotations. But those backwards annotations, they're just projection functions. And that means they're going to have a really specific type, and normally only a few inhabitants of that type. And normally, because we actually want it to project, just one inhabitant of that type. So I bet we could synthesize them, maybe using a tool like Google+. And even though I've just met you, I can tell that you're also passionate about making sure that the languages we make in this field are actually usable. And even though I've just met you, and maybe because I stalked you online, I know you've been working with the HCI group at Penn, so maybe we should do some user testing to make sure they're just as usable as normal generators. Gosh, maybe we should write a paper.
Sam, we already have written a paper.
Oh, yeah.
Thank you all for listening.
Plenty of time for questions.
So great talk. I'm Oliver from the University of Washington. I love the presentation style. So you said something really interesting at some point in the talk. It was that, given a bunch of example programs that all have some property or display some bug, you can learn weights that the decisions that led to those programs, mostly like weights on which decisions to make. You also said that you can shrink an existing program. How are these two concepts related? Can you use some heuristics or those weights on the shrinking part instead of generating similar programs? These seems to be two related techniques that are both useful, but I wonder how they are related.
That's a really good question. So concretely, these things are pretty separate, right? They're different interpretations of the reflective generator, and the shrinking happens purely on a structure of choices, whereas the example-based, I guess they both, potentially. A lot of this, now that we're in the domain of just manipulating choices, you can apply arbitrary functions to the choices and then go back forward. So yeah, I'm not sure. There could definitely be something there.
Yeah, it seems like something a little more principled than what, say, C-reduce does. And there's lots of heuristics there that, are very useful in practice. So yeah. I think exploring that might be interesting. Yeah, thanks.
Yeah.
Hello there. So one of the things that is useful to do sometimes when you're generating data types with invariants is to define a function that restores an invariant in a broken example. So for example, you might generate a tree labeled with integers and then prune it to get one that is a valid binary search tree. And that can be useful both at generation time, during shrinking, or in your case, if you consider an example that has come from the field. It might not be something you can generate, but perhaps you can fix it so that it is fixing up values so that they are generatable, something that can be done using reflective generators?
That's an awesome question. I am not, so the tricky thing is that if you try to reflect on a value that does not satisfy the invariant the generator maintains, then you don't get choices. What you'd kind of need is two generators that are in some way compatible, one that can reflect on choices in an invalid value, and then one that can go forward to fix up the choices and make better ones. I I want to think more about that. I'm not 100% sure, but like I think it's a great idea.
When you've thought about it, tell me what you come up with.
Hi, Jeremy Gibbons from Oxford. Thanks, great talk. Nice double act. But I'm a bit spooked about the partiality in the partial monadic things. You've got letters or numbers, you have to do a case analysis, so you write a partial thing for each case and put them together and happen to know that that covers all the cases. That feels to me like you're trying to squeeze into the lens format something that's not a lens, and in particular something that's better done as a prism, which are lenses for some types rather than product types. Did you think about that?
So it does actually use prisms when we do the lens side of like where we do, we use prisms for the backwards annotations.
Okay, so I need to go and read the paper.
Yeah. I just said lenses because, yeah.
Right, thanks for the great talk. I was wondering if have you looked into using this? What I see is, writing generator is quite painful, right? So and then, going backwards here is great. So I wonder if, I go through the pain of writing my PDF generator, and then I just grab a bunch of PDFs. They all go backwards, right? And then I can understand the distribution of the data. Have you looked into if you can leverage this into understanding the distribution of structured data by just running the generator in a backwards way?
We haven't done any analyses on the choices, choices from a set of things, but there's no reason you can't. There's a lot of flexibility because these are totally uninterpreted structures to either in the backward direction or as post-processing after to do analysis like that.
Okay, so I can have a generator that say, I don't know the probability for the choices, and then it will run backwards anyway.
Sorry, say that again?
So, right, so when I write the generator,
Yep.
right, if I want to go backwards and understand the distribution of the data, I cannot just assign probabilities because, I don't know that.
Right.
Right, so you say that...
Yeah, you would just write the
Okay.
generator without any weights. The backward direction ignores the weights, so
great.
you can figure out the weights after the
Awesome.
fact. Yeah.
All right.
Great. Thanks. Let's thank the speaker again. I think we've run out of time for questions.